Okay, so let's review what dilation is. Suppose that we have a point A, another point P, and we want to create a dilation of A with center of dilation P. That point will be called A prime. The way it works is we would take a line and draw it through PA. We would measure the distance from P to A, and then on that line that we drew through PA, we would plot another point A prime that is exactly twice as far from P as A is from P. Now that twice as far comes because we set the scale factor at 2. If we set the scale factor at 1.5, it means that A prime, the distance from P to A prime, is 1.5 times the distance of P to A. Suppose now we add a second point, and we'll call this point B, and we'll draw a segment from A to B, and we'll then create a dilation where we will dilate both A and B to create points B and B prime. Now a couple things you should notice here. First of all, the length of segment AB, which is 2.24, is exactly half the length of segment A prime B prime. In other words, A prime B prime is twice as long as AB. And again, that's because we set the scale factor to 2. If it doesn't look like it's exactly twice, it's because of rounding. So suppose we set the scale factor to 1.5. Well, now the length of segment A prime B prime is 1.5 times the length of segment AB. So this scale factor shows up in a number of ways. The distance from P to A multiplied by 1.5 gives the distance from P to A prime. The distance of P to B multiplied by 1.5 gives us the distance P to B prime. The distance from A to B multiplied by 1.5 gives us the distance from A prime to B prime. Now another thing that's worth noting here is that the slope of AB, in this case, is negative 0.5. The slope of A prime B prime is also negative 0.5. What that means is that segment AB and segment A prime B prime are parallel to each other. And that'll be important to keep in mind as we go forward. Okay, so now let's look at what happens when we, in this case, have a triangle. And so we now have 3 points that we've dilated, D, C, and E, and created D prime, C prime, E prime, which will change the scale factor, let's say, to 2. And in so doing, we've also dilated this triangle, ECD, to create triangle E prime, C prime, D prime. Now, one of the things you'll see, for example, CD has a length of 3, C prime, D prime has a length of exactly 6 when the scale factor is 2. EC has a height of 2, E prime, C prime has a height of 4, ED has a length of some number, we're not quite sure, but E prime, D prime is going to be exactly double that length. Notice though that the areas, when we compare them, ECD has a height of 3 times 2 divided by 2, or 3. C prime, D prime times C prime, E prime gives us, divided by 2, gives us the area of this larger triangle, but now we have 6 times 4 divided by 2, or 12. So the area of this dilated triangle is not twice the area of the original triangle, it's 4 times the area. And that's because we doubled the base, we doubled the height. So we had multiplied by the scale factor of 2 twice. So that means that the area of the new triangle is 4 times the area of the original because 4 is 2 squared. If we set the scale factor to 1.5, then the comparison of the areas will show us that this dilated triangle is 1.5 squared times the area of the original triangle. Okay. Now you can also see that we could take another figure, let's say a quadrilateral, and in this case we've changed the center of dilation, and so in order to find that center of dilation we can move Q and Q prime around until they're on the same spot. So you can see that when the center of dilation is one of the vertices of the figure, then the one figure will be completely contained inside the other figure. So if we go back and look at our triangles, we can see that if we take point P, the center of dilation, move it right on to C, that now the two triangles, the original and the dilation, are just inside each other. When the scale factor is set to 1, then the original triangle is inside the dilated triangle, where if the scale factor is less than 1, then the dilated triangle is inside the original triangle. And again, all the distance ratios hold. So distance CD is half the distance to C prime D prime because the scale factor is 2. The distance from C prime to E prime is double the distance C to E, and the distance E to D doubled is the distance from E prime to D prime. Again, E prime D prime and ED are parallel to each other. Okay, so here's an actual application of these triangles. Suppose that you are wandering the desert with a measuring stick and a tape measure, and you want to know the height of this pyramid here. Well, what we're going to do is we're going to use the shadows cast by both of these figures to create two similar triangles. And by similar, we mean that one of the triangles is a dilation of the other. So suppose you set your stick in the ground here, and your stick has a height of 5 meters, and it casts a shadow of 12.3 meters. So that would be the distance from here to here. Similarly, you measure the distance or the length of the shadow of the pyramid, and you find that it has a shadow of 150 meters in length. So now we have 3 measures for these triangles. We're missing only the measure of the height of the pyramid. So here's what we can do. We can say that the ratio of the pyramid height to the height of the measuring stick, that's our scale factor. Well, that also has to be equal to the ratio of the length of the pyramid shadow to the length of the measuring stick shadow. That also has to be equal to our scale factor. When we multiply both sides by 5 and work it out, we end up with a height of the pyramid of 61.01. And all we did was use the fact that these two are going to be similar triangles and use what we know about dilation to calculate the height of the pyramid based on the height of the measuring stick and the length of the two shadows.